So first of all, I'd like to say thank you very much, everyone, for joining us this morning to talk about defining intelligent system competence. So this is a webinar and a series that we're doing on autonomy. So thanks for joining this one. Hopefully in this discussion, we're trying to, this webinar, it is one way, so you can only hear us, but we want to get as much discussion going as possible. So there is a Q&A function, so I'll please encourage you to use that function to raise comments, raise questions as we're going through. We'll try and answer some of them as we go along, but we've got a dedicated session at the end where we'll talk about those questions in a lot more detail and add some discussion there. So before we get started, I'd like to introduce myself. So I'm Jake Rigby. I'm the Research and Development Lead at BMT. And we're joined today by two speakers. So first of all, we've got a special guest speaker, Alan Hunter. He's an academic from the Faculty of Engineering at the University of Bath. He's the co-investigator for a new accountable, responsible and transparent artificial intelligence centre for doctoral training. It's the new AI focus centre at the University of Bath. His main academic areas also include underwater sensing and maritime robotics. We work with Alan on a range of different topics, including this. And then for the main part of the presentation, the main speaker will be Chris Burnside. So Chris is a principal mission systems engineer and the system design and architecting capability lead. So Chris specializes in mission systems design and development and its integration into the naval platform. He has held system design authority and R&D roles for various maritime mission systems, and he'll be using that as part of his experience and some of his thoughts to talk about the topic today. So the agenda for today's webinar. We'll start off with a very brief and quick introduction to BMT. We've got a foreword from Alan Hunter, who will talk about the new accountable, responsible and transparent artificial intelligence centre at Bath. And then the main presentation will start at about 10 minutes past. We'll be talking about the concept of AI, what an intelligent system is, how we can start to define that point of release and the social expectations around that. And then we'll wrap it up with some case studies and some examples of what's happened so far. We'll be capturing any questions as we go along, but we're finishing off with a dedicated discussion topic at the end, so answer any questions then. So first, very quick introduction to BMT. BMT is a global engineering risk, safety and management consultancy, working on a range of topics from ship design to software development. We are independent, so we're an EBT similar to John Lewis, and we're also independent from manufacturing sites, which allows us to provide impartial customer friend and guidance roles. So this diagram shows that we've got kind of global presence with little blue diagrams showing either where we have an office or a customer around the world, and that varies anything from ship submarine design, specialist designs, that can be luxury yachts. We've got an office in Southampton dealing with those, and mining machinery in Canada, Australia, even to things such as water and environment, where we provide environmental surveys and flood and climate resilience modelling services. So the part of the business that we're really representing today is BMT Defence and Security UK. We've got around 500 people in the UK and a trusted independent partner for defence and security sectors. Some of the key projects that you might know us for, working with the Metropolitan Police on their business transformation programme. We also worked as part of the Aircraft Carrier Alliance to help design the Queen Elizabeth class aircraft carrier, and we did the basic design for the Tide class tanker as well. We're also working to maintain the Royal Navy's in-service submarine fleet through a lot of our asset management services as well. So that's it for the main introduction. I'll just hand over to Alan Hunter, who's going to give a quick introduction to the new Centre for Doctoral Training at the University of Bath, which will set the scene.
Okay, good morning, everyone. Thanks for inviting me along to your webinar. I'm very interested to sit in on the talk and the Q&A session afterwards. So as Jake mentioned, I'm involved in this new doctoral training centre at Bath on artificial intelligence. So to provide a little bit of context, the UK government's been putting a lot of money into developing future AI researchers. And about a year ago, we bid into a CDT funding scheme and won £7 million in funding to develop a centre for doctoral training. So this funding is going to go towards training over 60 PhD students over the next 8 years. And we're following one of the sort of common PhD programs that are common these days, where it's a 4-year PhD. The first year is a taught year, so in that year the students do a Masters of Research, and then in the final 3 years they do their PhD research topic. So our approach that we've taken in this centre is to span across multiple disciplines. So we figure that artificial intelligence isn't just confined to computer science. It has relevance in applications in engineering, and implications in terms of social scientists. So we're coming together as 3 different disciplines with the one goal of developing artificial intelligence solutions. And our sort of motto, if you will, is that we're training specialists with perspectives. So we're bringing in students that are trained in one of these 3 disciplines. They'll become specialists in AI in this particular discipline, but they'll also have a perspective on the other 2 aspects. So I'm in engineering, so I'm interested in developing robust AI solutions for engineering applications. But obviously, any student that I want to train has to have knowledge of the sort of cutting edge techniques in AI. So that comes from the computer science side of things. And of course, anything they develop is going to be related to future policy and regulation and so on. So that has a big impact from the social science side of things. Next slide, please. So there are some sort of guiding principles that focus our centre, and that's where the artificial, accountable, responsible and transparent keywords come in. Sort of really more relevant in the other order. So transparency, accountability and responsibility is the order that makes more sense. So one of the problems with AI up until this point is it's been very much a sort of a black box approach. So people have been developing AI solutions and using neural networks and so on, and it's not necessarily clear how they're making the decisions that they make, and this is a bit of a problem. So one of our sort of guiding principles is transparency or explainability. We want to break open this black box and allow the AI to explain what it is it's doing, how it's perceiving its environment, and how it's making decisions to take action within the environment. And if we can do this, then that means that we can make the system accountable, right? So it's able to explain its decision-making process. And if it's accountable, then we can use it responsibly, and this will lead to trusted and ethical use of AI systems in society. Next slide, please. So as mentioned, this is a 4-year PhD program. So in the first year, the students are doing completely a taught course. So they have to do various taught units and participate in group projects and so on. And during this year, they also develop their research questions that they're going to develop over the next 3 years of research. And then over the next 3 years, they'll really focus on solving their research problems. But throughout the course, we'll also sort of continue to develop their skills, get them involved in public engagement, put them out on placements with their sponsors, and so on. So we're really sort of keeping them engaged with our partners. Next slide, please. So just to sort of briefly outline this first sort of taught year. In the taught year, a student comes in from a particular discipline, computer science, engineering, or social science. And so typically they'll take advanced courses in that particular discipline, and then they're able to take introductory or advanced courses in the other disciplines. And so what we do is, depending on what their particular area of interest is, we'll make a sort of program of study that will sort of maximise the value for their PhD research. Next slide, please. So as I mentioned, throughout the 4 years of research and study, we're keeping them engaged with industry and partners and so on, with various events. So we're going to hold writing retreats and summer schools and guest lectures, a little bit like this webinar and so on. And just one example, we only started about a year ago, but one example that I can talk about is the AI Challenge Day, where we brought together a bunch of members from industry together with the students, and we sort of we discussed and defined the big challenges in AI. And BMT, for example, were involved in this game. Next slide, please. So here is our first cohort of students. We have about 10 students in this cohort. They started last September. They've gone through their talk year. They've all been trained up on AI methods and all the things that they learned in their talk component of the course, and they're just embarking now on their research topics. And roughly it's a third split between engineering, computer science, and social science. The next cohort's being recruited. They'll be starting very shortly in September. And so we'll have over 20 students already on the program in about a month's time. Next slide, please. So I just want to finish by saying that it's not just within the university, this CDT, we're sort of involving the greater environment. So we're working with industry partners and also other partners from government and various other places. And here's a sort of just a list of all the partners we have on board already. And our aim is for each of our students to work with these partners to solve their particular problems. But you can see that BMT is in the list there, and we're hoping to define a project with BMT very shortly. So I won't talk for too much longer. But if you are interested in partnership, if you're not already a partner, then please contact me after the webinar, and I'll be happy to discuss the options there. So I'm very interested to see the next talk on competence and AI. It's very much aligned with the principles of our centre. So I'll hand back to Jake.
Brilliant. Thank you very much, Alan. That was really nicely setting the scene and sets an example of one of the few academic research projects that we're working with. And as you said, it links to really nicely with the main talk that Chris is going to do. And yeah, something that we're always trying to do, provide that academic link, but then also the kind of our industry view and how do they work together. So hopefully with the discussion at the end, and if you can stick around, then we can kind of discuss that a bit more. So without further ado, I'll hand over to Chris for the main talk.
Many thanks, Jake. First of all, many thanks to everyone who has taken the time to join this discussion today. I do hope it is fruitful for whatever reason you have for attending. So why are we here? Artificial intelligence, we have all heard of it. We might not necessarily know what it is or how it will revolutionise our world in ways talked about the world over, but it exists and it is here to stay. This slide is by no means comprehensive, and I have merely carefully selected a small subset of some of the stakeholders who have a vested interest in this concept of artificial intelligence. This group, along with many other parties, have generated a wealth of analysis and commentary in recent times on the very subject of AI, addressing a spectrum of topics, and largely they are very bullish and optimistic about the technology's credentials and potential for bringing about change which benefits large walks of society. So how plausible are some of these big ideas, and how do we go about making them a reality? The statements within the speech bubbles around the outer of the slide have been well publicised, and they are credible on first inspection, but are they viable? One thing that has been playing on my mind since the start of this year is this notion of system competence, and how a system with high levels of intelligence and capability can be formally readied for the real world. In other words, how does one define the point at which the system is self-sufficient and self-sustaining? This session specifically looks at these qualities and the challenges arising from trying to determine the points at which this state is achieved within highly intelligent systems. Throughout, you will hear reference to these three terms on screen. It is therefore worth outlining what I mean by these terms in the context of this discussion, given the range of possible meanings and interpretations which, whilst all valid, may not quite fit here. By competence, I mean a system which exhibits the characteristics and skills to sufficiently fulfil its role within the environment in which it is deployed or employed. The concepts of capability and capacity are also closely aligned. Arguably, they could be used interchangeably, but I have settled on competence here. Self-sustainability and self-sufficiency are of course synonyms of one another. The distinction I make here is that the former centres on the system's ability to look after itself, whilst the latter defines the system's ability to continue to look after itself indefinitely, essentially remaining self-sufficient indefinitely. So please do bear this in mind as we progress through. But before we begin in earnest to explore the concept at hand, it is worth clarifying what this session is not about. As discussed over the preceding slide, much analysis has been undertaken by many of the outlets cited on topics such as trust, transparency, ethics, and the revolutions on offer to enterprises through the adoption of intelligent technologies, and so any commentary I were to deliver here would merely be lost within the swathes of material available out there already. Make no mistake, these topics are fundamental to the introduction and long-term enduring effectiveness of artificial intelligence and its applications. But I have elected to leave the thinking in these areas to others whilst we explore the subject from a slightly different perspective. I should also state that the thoughts generated are application and domain agnostic, and this has specifically been employed given the global nature of the concepts discussed, as well as emphasising the collaborative effort required across industries and borders in order to elevate intelligent systems' place within the appropriate corners of society. So as the slide states, this is not a conversation on trust, although there is definite lineage with that subject, or ethics, or to try and make the case for why intelligent systems should replace human beings or why they shouldn't, and nor is it delivering research findings on the differences and similarities in cognitive development between a human being and a machine. As stated previously, these are subjects well trodden, and so I shan't explore those here, but let me reaffirm that there are relationships with these topics. Throughout, I speak of this concept of a highly intelligent system. So what do I mean by this? Well, we are referring to those artificially intelligent systems with high levels of and near full autonomy, levels 4 or 5 for those familiar with level of control definitions, which are monitored and autonomous respectively, with the ability to make their own decisions with very little, if any, contribution from a human being. Typically, in complex environments where there are many variables, high probability of unpredictable behaviour, and high-profile, high-impact decisions to be taken where errors or misjudgments are likely to result in damaging consequences. I term these multidimensional systems. For example, an autonomous car would be classed as a highly intelligent system via my categorisation scheme, as would the autonomous naval platform on screen. The range of system complexity is vast, and therefore it is not plausible to define explicit measures and bracket applications within particular categories. So this outline definition provides an adequately informed baseline from which to understand the concepts discussed throughout. On that note, measurement of autonomy and intelligence is another challenging area of study, which does closely relate to the topic of competence determination under review here. In the context of artificial intelligence types, quoted in literature you may have read, we're referring to those machines or systems that sit within theory of mind and self-awareness. When assessing the capability and development of an AI system, you may find it is compared to that of a human being. But is this an appropriate and informative analogy? As human beings, in our early years, we are largely measured against elapsed time and time-defined milestones, with an expectation that by certain ages, we should have developed a level of maturity commensurate with the experiences endured in that time. Looking at this timeline, for example, from the point at which a young adult enters the working world, typically they will go through a number of phases and gates in order to develop and prove competence, and subsequently see their levels of authority and autonomy enhanced. Now, progress to these milestones can sometimes be subjective, and many professionals do not undergo formal examination of their capabilities in the same way as they'd have done through their educational years. Largely, they are judged on their performance in real-world application as they serve their time. But an elapsed period of time does not necessarily equate to adequate competence in date with current demands. And indeed, for many, there's an expectation that they will proceed on a journey of continual self-teaching in order to maintain currency of knowledge and skills, and ultimately their competence for the role they assume, some of which we present a challenge to formally test for. Of course, each and every one of us present here today will have gone through different journeys on different timelines to arrive at the position we currently find ourselves in, and the reasons for this are wide and various. But staying on the subject of competence, we should be there in that role, as we have categorically demonstrated that we know what we are doing and we are suitably prepared for any challenge falling within the bounds of our area of operation. It is simply not viable to ready an individual for every possible eventuality they may encounter throughout their lifetime. This recent pandemic is a case in point of that. However, by their very nature, human beings are versatile, they are resilient, and they are highly capable. That said, experience tells us that in the face of adversity or immersion within a world for which we were not prepared, that there is no such thing as damage-free, and there are always consequences causing some degree of detriment. The real value is in establishing how to minimise those consequences and the harm they inflict. Let's now extend that train of thought to a highly intelligent system, where the development process is completely different and will demand a more rigorous and comprehensive timeline of events. Can time be taken as the dominant measure against which an intelligent system's readiness can be deemed? Initial feelings would suggest not. The number of cycles or iterations required to be performed before a decision point can be successfully passed cannot be reached based purely on hard and fixed time-defined milestones. In the cases of both the nurturing of a human being, there is no blueprint. There is of course swathes of advice and learnings from experience, but there is no set global protocol to developing capability within a human, because we're all different and living in different worlds where circumstances, demands and tests vary starkly. The same can be said for intelligent systems, and as new developments are introduced, it is not only in their primary function in which they will differ, but their capabilities will need to be tailored around the operating environment and the expected changes within their local domain, as well as wider society. A level of competence must be nurtured and demonstrated to assure that the system is fit for deployment. But how do we as scientists, engineers, designers, users, consumers, critics, and the general public define this point of readiness? Looking again at the qualification timeline, the stark differences in achieved milestones on the measure of elapsed time can be observed. And of course, it should be pointed out that the scales of both timelines are not the same. And this is not meant to compare the cognitive development of a human and machine. It's important from the earlier introductory slide on scope that I re-emphasise this. It can take tens of years for a human to be relied upon to satisfactorily complete some complex tasks autonomously. And they are often always required to prove this competence before they are entrusted to proceed and then subsequently judged throughout. A highly intelligent system, on the other hand, is expected to perform its full capability and perform it impeccably. And the human user and wider society are expected to have confidence in the system. Is this a realistic scenario? Do the beliefs of it's about there or it's good enough apply as they do to human beings in many cases? What are the fundamental questions behind reaching this decision point of sanctioning a highly intelligent system to enter the real world and operate with autonomy and high levels of authority then? Where the human has very little, if any, responsibility in the activity sequence, one must prepare for the reality that designing for the system's primary desired function or collection of functions is not sufficient. The system needs to be designed to deliver those functions in a complex, ever-evolving world 360 degrees around it, where it may have to react or adapt in order to continue to fulfil its obligations within conditions out with its control. Let us first derive some criteria required to inform the system design and development cycle, promoting as much natural capability as possible and nurturing additionally required capability as early in the development cycle as possible. Here, the criteria suite has been grouped under 4 headings, which we have deemed to address a series of considerations fundamental to satisfactory system introduction. Operating profile. One of the most important questions in the early stage of any development and design programme is what is it one is trying to do, and subsequently, is one selecting the best route to solve the problem? Within this pillar, we require absolute clarity on what the purpose or function of the system is and the environment within which it is expected to operate. Should the bounds of this environment change or be breached, we must understand the possible eventualities to ensure the system is capable of reacting and responding appropriately and proportionately. This extends to evolutions in operating landscape. Whilst we cannot possibly predict the change the future will bring, we must deliver well-informed predictions in an attempt to future-proof our assets. Performance measurement. It goes without saying that it is essential to fully understand the capability of the system, but equally, and perhaps in this case more so, its limitations. So when it comes to performance and understanding the system's ceiling, we need to be able to satisfactorily answer a series of what-if questions. As stated earlier, when talking about the human being, we cannot prepare for every eventuality. There will always be unknown unknowns out there, but we must ensure full preparedness for what we do know, so that we deliver a system with behavioural characteristics that are appropriate for the environment. This also extends to levels of error and tolerance in the context of how far left, right or back from ideal the performance can sit before the risk of an adverse outcome happening becomes unacceptable. Of course, this margin for error could be widened with the deployment of a human-machine team, but here we are focused on highly intelligent systems with little to no human support. Third-party dependencies. A pillar with the potential to make or break the full realisation of a highly intelligent system's promise. Whilst an intelligent system inherently relies and depends on multiple components which make the system what it is highly likely that it will depend upon external influences to complete and/or enhance its capability. This demands that due diligence is undertaken on any proposed supporting act to ensure system performance and/or behaviour is not compromised, which could raise some interesting conundrums when it comes to architecting and user interoperability, for example. Technology deficiencies, be it inherent within the system itself or due to shortfalls of third-party service providers, must remain transparent throughout the development, design and deployment cycle for the purposes of maintaining goal currency and application suitability. This extends to the ever more precarious subject of integrity and sustained protection, what with the repercussions of such an adverse event taking on potentially greater severity given the ever-improving capabilities of adversaries and levels of connectivity. Additionally, the impact of commercial aspects, such as scheduling, review and business process, must be ingrained within the design and development programme to ensure any constraints arising from such factors placed on the system design are exposed early. Beyond deployment, we spoke earlier about future-proofing and trying to determine how the system operating landscape may change in the future, and this is not easy to do. However, the designer, in conjunction with the user, must endeavour to create a solution that is capable of remaining self-sufficient and self-sustaining through periods of change which are inevitable, and largely this can be challenged through the definition and subsequent resolution to what-if scenarios, including the identification of last resort contingency measures. This is not to say that upon first deployment design work stops, but the system design should be such that it can maintain currency and fitness for purpose without the need for substantial intervention. Of course, the term substantial is open to interpretation from the perspective of quantification. But what we mean here is the need to undertake a timely and costly overhaul of elements of the design to fundamentally change the system behaviour and/or function suite. That said, it should be accepted that there will come a time when the system is no longer sharp enough, so to speak, for the challenges of the day. But it is highly desirable that the designer can provide an indicative forecast on this, and that the user can be clear on the conditions that will officially determine this point in time. This should feature as a milestone within a comprehensive schedule of through-life upgrades or updates. Clearly, this conundrum is multifaceted with respect to the influencers associated with satisfactorily solving it. The criteria derived here are merely a subset of a wealthier collective of checks and balances, some of which stand independently, and many are interrelated and interdependent to or on one another. The complexity will vary between systems due to the differences in functionality they are designed to deliver, and indeed the expectations placed upon them. For example, a system moving a box from point A to point B, let us refer to this as a one-dimensional system, is relatively simplistic in its design, holds very little responsibility, and the risk of an adverse event occurring is negligibly small. Therefore, the route to release into society is relatively smooth. Conversely, let us look at a system handling multiple streams of information or data simultaneously and making decisions based on this received intelligence, say in a warfighting context, multidimensional in nature as I have termed it. In this case, the system is comprised of a network of systems and interfaces afforded a high level of responsibility with the risk of an undesirable and catastrophic event taking place being very real. The route to release is much more complex, featuring many more gradients making the self-sufficient and self-sustainable declaration point orders of magnitude more challenging to distinguish. Allow me to further explain by way of an example scenario. Let us take network-centric warfare as our datum. Here, let us assume this naval combatant circled in red is a highly autonomous platform, a highly intelligent system in this case, with the authority to make combat decisions. So implications of mistakes or errors of judgment have potentially severe consequences. What does this highly intelligent system have to think about and contend with? Of course, all the criteria described within the preceding slide are crucial. So what about some of the specifics for this particular application? The system is a network within a wider network, able to exploit a wealth of intelligence from a spectrum of sources, both hosted and third-party, so as to manage and act upon a deep and constant information flow, which could be changing at a high rate. It has to think about what the other elements both within and out with the network are doing, how are they behaving, and what might be their future intentions. It must understand the environmental conditions and the implications if these change, for instance on sensor performance and the limitations it could present to its decision-making ability. Should it be deploying off-board assets, which in the image presented is the case, it must command and control these simultaneously, with each perhaps undertaking a unique role in the air, on the surface, below the surface, or on land. Clearly, this is a complex scenario, where the system must demonstrate competence across multiple axes and act decisively where change could take place rapidly. This presents a significant challenge in declaring such a system ready for such a deployment, given the high levels of variability and unpredictability. The route to a state of system self-sufficiency and self-sustainability is fraught with a series of hurdles. So how does one clear said hurdles? Logic would suggest that such a scenario would require incremental development, with a prolonged handover period from a human to the system, with the human relinquishing more and more responsibility as the system matures. But two questions arise. What is the trigger point at which the system is handed more autonomy, and when does it end? At which point is the decision made that the system can no longer be afforded any further responsibility? It may be that a state of full autonomy and authority can be reached with human hands and eyes off. But is this realistic, or are we destined to always see a teaming arrangement of some sort, even if the human is performing nothing more than a watching brief? What can be safely said is that for an application such as this one, that self-sufficient system in this environment is some way off, and it is likely that a sequence of incremental steps over a prolonged period of time will be required. What do we believe this all means for conventional design methodologies then? Arguably, very little theoretically. However, it is likely that the system design community may have to refine and reposition rather than redefine current methodologies. In the early phases of intelligent system development, progress is likely to be made iteratively and in increments to ensure a suitable and indeed achievable direction of travel is maintained. That said, there is a time pressure in the context of the outside world changing and the system maintaining its route to readiness and a state of self-sufficiency and self-sustainability. So there is a delicate balance to be struck, getting the design right and releasing the system too soon or too late. This balance presents a challenge commercially. We are increasingly seeing demand for solutions of greater capability delivered in ever-shortening timeframes. The practices adopted, the milestones defined, and the deployment routine are most likely to take on a different look and feel to what we would currently understand as traditional, but the underpinning theory should remain largely the same. Without question, test and evaluation are fundamental to the successful design and deployment of any system or product, and in the dawn of highly intelligent system development, this is no different, and if anything, will take on ever greater prominence. The approach of test and achieve is likely to be more and more of a necessity, as opposed to test and declare, whereby deficiencies and shortcomings would require review and refinement of capability goals. In line with the discussion up to this point, what is being tested for and against is required to be indubitable, with associated caveats, constraints and conditions plainly noted. Modelling and simulation will inevitably feature as a cornerstone of the test and evaluation regime. Multiple real-world scenarios will firstly require careful and comprehensive definition applicable to the system under development. This is all reliant on the designer, the consumer or user, and all associated stakeholders, be it within legal, regulatory or other circles, maintaining a grasp of the operating landscape today and potential near to long-term manifestations from tomorrow. On the theme of this point, the ideal is for a system to be able to self-learn from experience, much in the same way as a human being does, but not at a detrimental cost, and within a time frame that ensures shortcomings or mistakes are not induced repeatedly. Generally speaking, as a society, we are expectant on people as individuals and human-centric enterprises to perform and behave appropriately, technically, legally, morally, ethically, with fairness and with due consideration for the wider world within which we live and operate. It is fair to say that as a collective, we expect a lot from each other. Over the long course of history, there have been many an occasion when human performance or behaviour has fallen short of these expectations, sometimes with catastrophic and indelible consequences, and society's ability and willingness to tolerate and move on has been stress tested to a great degree, which continues today and will do so long into the future. So to that end, when thinking about intelligent systems and their potentially foremost role within a new, highly artificial intelligent society, does one expect the human race to demand and expect more or less than they do from their fellow beings? If we as human beings expect more from an intelligent system than we do from ourselves, then the art of defining and declaring adequate system competence and readiness becomes all that more challenging. In this context, self-sufficiency and self-sustainability take on something of an elevated and uncompromising meaning. History tells us that one instance of a machine or system failing is enough to eradicate public confidence entirely, resulting in the removal of that capability from society. And so either we have to be willing to be more lenient and patient in the early phases of intelligent system instruction, something which it is fair to say is in ever-shortening supply in the corporate world, or we need to ensure our systems are bulletproof with near perfect levels of confidence that they will not let us down. How do the system designer and the subsequent users or consumers achieve that? Technological evolution tells us that anything is possible where there is a will. However, in an ever-changing and unpredictable world, can an intelligent system stay ahead of the curve long enough to merit its introduction in the first place? A prime example of this inequality of expectations is the case of the 2018 Uber self-driving car fatality. In this instance, a woman was struck and killed while she was crossing the highway with her bike in the middle of the night. This was a truly tragic accident, causing international disbelief and controversy. However, it has still to date been the only example of a fatality from a level 3 self-driving car. Every year, road accidents claim the lives of 1.3 million people worldwide. By comparison, and as a percentage of driven miles, autonomous cars have proven themselves to be vastly superior in terms of safety performance. Given this information, why is it then that in a recent survey from March 2020, over 90% of American people said that they did not trust self-driving cars? How many test and demonstration cycles need to be undertaken before a globally acceptable standard has been reached? Are we in the space of only accepting perfect performance for highly intelligent systems, noting that defining perfection is no mean feat? The evolution of the autonomous car has been in progress for some time now, and yet here we are in 2020, and we do not yet see our roads lined with such technology. The point of readiness has not yet been reached. This now leads me into my next point. We'll all be familiar with this aircraft, still today one of the most revered engineering feats of our time, and yet it has been off our runways since 2003, and most poignantly of all, nothing has replaced it. In 1969, Concorde was a groundbreaking, literally revelation, a masterclass in innovation and making the most of technology and human willpower at a time of complex cultural and political trends. Like Concorde, highly intelligent systems applied across society have the potential to revolutionise how we do business. But unlike Concorde, let's be sure that we can harness it for the long term. Of course, this depends on a myriad of factors, not only this notion of competence definition. Concorde fell out of favour largely due to the economics of its upkeep, but a few well-publicised safety-related events didn't help its cause either. And this references back to what we discussed earlier around the high expectations placed on technology by society. This world is changing and at a brisk pace. The ability to innovate is encouraged, but increasingly it could be argued that this is required to take place under ever-tightening constraints as we see matters such as globalisation, smart everything and sustainability take a more prominent place at the forefront of our minds. This then runs the risk of us suppressing the possible and not enabling us to fully realise the potential of capabilities such as highly intelligent systems, with them never quite being as good as they could be. But this is where the subject of this discussion is headed, in an attempt to pose the questions which may support in trying to avoid this no better than satisfactory outcome, or worse still, another Concorde moment. If you were the one with the clipboard and the red pen, so to speak, what would you need to know, see or do before you signed your name on the dotted line to sanction that system to enter service in whatever capacity it had been designed? Or if you were someone whom had to work alongside or depend on a highly intelligent system, what would it require for you to be content to do so? We'd be very keen to hear people's thoughts on this. Some final words from me. I appreciate that this session may have been more philosophical in nature and has provided more questions than answers, but hopefully it has facilitated some deep thought within you all, which you can take away to assist you in further understanding how intelligent systems may or indeed may not work for you and help shape your direction of travel, be that in system design, acquisition, collaboration, or simply in your role as an interested observer. To coin an old cliche, I believe there are no right and wrong answers here in how to determine high system maturity states, and even whether we should be all that concerned with the question at all. There are a number of subsequent debates and notions that spawn from this initial foray, but hopefully this has generated some food for thought among you all, and I implore you to pitch in with your views. I should also state, with regard specifically to the note on regulation, that BMT Defence and Security are a member of the Maritime Autonomous Systems Regulatory Working Group, which includes industrial and regulatory body partners. This session has not explored regulation or indeed the purpose of the MAS Working Group, but a presentation on this initiative is to be delivered at the International Naval Engineering Conference at the beginning of October by Chloe Wooster-Smith. Please do also read the associated paper, which does develop further the points discussed here, as well as looking at other compelling matters of interest, such as the possible stance of our adversaries and whether these systems will be nationally identifiable when it comes to their makeup and behaviours. That just leaves me personally to say many thanks to you all for taking the time to listen today. And with that, I now open the conversation to the floor, and over to you, Jake. Thank you.
Brilliant. Thank you, Chris. So you've heard our view now. We've heard a little bit from academic view from Alan. Now I'd really like to hear your view and your discussion points, particularly those in government, frontline commands, maybe from regulating bodies. Yeah, everyone interested to hear your points. If you have any questions or comments, please send them through on the Q&A. So you've got one that has been published, so saying to determine the various potential scenarios encountered by the overall system of systems, including the deployed AI system, we need to resort to a better systems engineering approach and identify all the hazards that can arise due to various interactions. Post-deployment, would we need to constantly monitor for new hazards due to the AI system learning more in the operational environment? So, Chris, any comments on that and having to relearn for the operational environment?
Thanks, Jake. Great question. My belief on this is that, put simply, is yes. The point that obviously has come throughout, or should have come throughout this presentation, we all know that the world is an ever-evolving place, and increasingly it's evolving at a higher rate of knots. So I'm firmly of the belief that there's an element here as part of the initial design phase where you take how the environment looks at a point in time, and that's only true for a point in time, and in likelihood that period of time is quite short. So there's a need for the design community, as well as the user community, to understand ahead of time, as difficult as that might be in some cases, to understand how that environment may evolve or indeed revolve with time moving forward, and what that means from the system's functional applicability and suitability, and indeed its behavioural traits. So there's this notion that the system itself will learn from experience, and we'll go on a quest of both supervised and potentially unsupervised learning through life. However, the ideal nirvana scenario is that that system is fully self-sufficient and is fully self-sustaining, with the need for human intervention to be almost net zero. So, in my opinion, in response to that question, I believe that there is got to be some sort of through-life quest and through-life assessment of how that environment might change and evolve over time. And obviously that depends very much on the application. So if we look at the autonomous car as an example, if we look at the example we spoke about with network-centric warfare, these are very, very complex environments that are likely to change radically as we move forward in time for various reasons. And there's a plethora of factors that will drive that, some of which we can predict now. There are others that frankly we won't be able to. But I think that's ultimately where the challenge in this comes in, is can you ever reach that point where the system can go about its business over a prolonged period of time without the need for that level of intervention, where you've got to effectively look at redesigning, re-architecting, or indeed retiring a system because it just isn't capable of meeting the challenges of the day. So my view, very simply, is I think yes, and I think it'd be interesting to hear what Alan's views are on that particular aspect. but this is the worry for me, or the concern for me, is that we run the risk of potentially stymieing that potential, because you can never quite get to the level of confidence to say, yep, we know technologically the system can do this, but can we have have we got enough belief to ensure that it will act appropriately and proportionately at all times?
Yeah, because as you're saying, you can never design it for every single scenario. So Alan, any thoughts on this?
Yes, I mean, I echo the thoughts of Chris there. So I think it's unrealistic to think that we can design these systems to account for every potential scenario that they're going to encounter. Right? It's just unrealistic. And in the field, they refer to edge cases. So there's always some unexpected situation that can arise, and you can't train for those kind of things. So I think, yeah, it's not a matter of building the system and then deploying it and letting it go. There has to be some kind of feedback there. It has to be either learning from its experience, or going through some kind of retraining process. I think there's kind of a balance here, isn't there? So you can either design a very, very constrained autonomous system, a very rigid autonomous system that's going to behave quite predictably in the environment, but it's going to be very limited in its capabilities. And on the other end of the spectrum, you can design a system that has a lot of versatility with a lot of degrees of freedom. It's going to have the capability potentially to adapt to more unknown situations, but at the same time, you're taking a risk when you deploy that thing, aren't you? So it's a really tricky question to answer there. There are so many different things to unpack.
Brilliant. Okay, thanks, Alan.
I think, sorry, Jake, if I just come in there again quickly. I think this concept of understanding the environment is absolutely crucial. And of course, there's a dependency on the design community, but equally, and perhaps more so, there's a dependency on the user community, in that they don't perhaps try and stretch the bounds of what is possible. And by bounds of what is possible, I spoke about ring fencing the environment. So understanding what the boundaries of the environment are you're operating in, and ensuring that the user community doesn't take it upon themselves to redefine those, or indeed breach those. As Alan rightly said, preparing, as with human beings, preparing for every eventuality is simply not feasible. But this is where that element of understanding the environment in which you're operating is absolutely vital, just as it is with human beings, but even more so in this context, so that there's a level of awareness and knowledge of, right, we've got a high degree of expectation of what might ensue here, and therefore we can prepare as appropriately for that. When we look to then broach those boundaries, or expand or extend or refine or redefine that environmental space, we then run the danger of going back into the sort of left-hand side of the V, if you like, to look at elements of redesign activity in order to redefine how that system behaves, in order to operate in this new sphere. So that element of understanding the user environment as well as the user's intentions is absolutely pivotal.
Yeah, I agree. Okay, we've got lots of other questions, so I'll try and pick some out. There's one comment from Anonymous, picking on the social expectation side and saying, do we only see intelligent systems as valuable if they can solve every problem we have and better us in every way? I think that's commenting on the high expectations that we have on those, which I think we agree. There's a question here about human-machine teaming, which I think was always going to come up in conversation. And it's someone from a high complexity controls and automation world, and they're asking how we think human-machine teaming or human AI teaming will differ from what has been kind of done already in the modern automation world, automation systems. Any comments on that, Chris?
So clearly, there are qualities that a human being can bring, and equally there are qualities that a system can bring that one another don't offer. or not offer, or indeed the opposite can improve on and can enhance. So the challenge is to strike that that sweet spot where you optimize your teaming arrangement, your teaming makeup, the constituents of your team, in order to get produce the optimal output. Now, that optimal output might be doing things more quickly, more efficiently. It might be actually, improving safety credentials. It might be improving security credentials. It might be, greater throughput, whatever it may be. And the art is to understand, well, okay, what can the system offer, but what are its deficiencies in that context? And indeed, what can the human being offer, and what are its deficiencies in that context? I think with intelligent systems, it sort of links back to the comment that you mentioned, Jake, just before you asked this question, is that what we have to try and ensure, and I think I said this towards the beginning of the presentation, artificial intelligence and high levels of autonomy and authority, or systems or capabilities with high levels of authority and autonomy, should not be solutions that are looking for a problem. They bring a degree of possibility and a very high level of possibility and potential, as do human beings, and arguably in many applications, some of which we've touched upon in this talk. In all likelihood, the best solution is a human being or a group of human beings married up with a complementary system capability. And I think it's probably fair to say that when you look across the myriad of factors and the myriad of inputs and criteria that need to be considered, that is in all likelihood probably going to be the most optimal answer, the most sensible answer, the safest answer. And again, that's all depending on the application space. With regards to automation, in my sort of outline, so I spoke about this concept of measurement of autonomy, or measurement of intelligence, and I gave a very sort of crude outline view on how I bracketed what a highly intelligent system is. Now, clearly, there are a number of potential measure points throughout that scale. I spoke about what I term one-dimensional systems, which probably relates more to the space of automation, where the environmental boundary is quite well contained. It's very well defined, and perhaps not a lot can really go wrong. And if it does, you're not going to see ramifications that are going to inflict severe, highly damaging consequences. So you've got that's the end of the scale, which probably is towards that left-hand side. And then on that right-hand end of the scale is where you're looking at, the example I gave around a naval combatant in operating in a task group, where the environment's much wider, where the levels of unpredictability are much higher. There's a lot more that essentially can go wrong. So between those two, you're looking at some, as I described it, sweet spot, where you look at the benefits and possibilities within each end of those scales and say, okay, you're probably going to sit somewhere in the middle. So you're ensuring you're trying to leverage and exploit the benefits, but also try and mask the deficiencies that each end of that scale actually bring.
Yeah, I think that's a good point. I got another question for Alan here, saying, great mentioning about the importance of transparency within AI, but how do we think this applies within military applications, specifically in regards to sensitive applications? Alan, have you got a comment on that?
Well, so it relates to the question before about human-machine teaming, really, doesn't it? So if you have an autonomous system within your system of humans and autonomous systems, then they need to be able to communicate with one another, and there needs to be some kind of transparency there to understand what the autonomous system is doing. So I think transparency, however it's implemented, and I don't have an answer for that right now, is absolutely crucial for making these systems trusted. I think just to sort of touch on a previous point, I think there's it's important to make a distinction between human intelligence and the system intelligence that we're talking about in this seminar here. So human intelligence is a very general intelligence. We are trained in a large number of different things, and the systems that we're talking about here are much more specialized. So, for example, as a human, I can, I learned to ride a bike when I was younger, and then I could transfer some of those skills across to learn to drive a car. Playing sports gives you abilities to react quickly when you're driving a car and so on. Whereas an autonomous car doesn't have that more general intelligence. So I think the value of human-machine teaming is the mixture of that specialized intelligence that a system can offer, and really precision and very, very high performance in a specialized task, versus the human intelligence, which isn't as specialized but can adapt much more quickly. And there needs to be, sort of going back to the transparency point, there needs to be some form of transparency in the autonomous systems to make that interaction work. Transparency from a human point of view is we're not very transparent or intelligent systems either, really, but we can communicate with one another, and that's how we can infer the thoughts and intentions of our colleagues and peers. Does that sort of answer that question?
Yeah, I think it does. I think that's a good response.
Jake, can I just quickly come in on that one as well?
Yep.
I think it's a really good question. I think that when we talk in a military context, when you're making combat decisions, you're absolutely right that if you've got a system that essentially is gathering intelligence and making combat decisions based on that intelligence off its own accord, you're absolutely right that understanding the mechanics behind the decision point that it has reached is absolutely essential. Clearly, in gathering the intelligence, when you look at, if you take the electronic warfare domain as a prime example, intelligence in that space is highly, highly desirable for many, many reasons. Real-time updates to signature libraries and being able to disseminate data and being able to filter out noise and put it onto a console in an operations room for someone to sit and make a decision on is great. Do you need a degree of transparency in that? Probably not. Probably not a high level of transparency. But where you then, as you're alluding to, where you're then getting to that system of systems where a kill chain essentially, and you're looking at all those building blocks, you're right. You need to understand. Well, okay, so if we take block A, block B, block C, block D, how's it arrived at this answer out the other end? And so it is absolutely, and this is where the human machine teaming argument comes up again, where that is a very, very you're highly constrained and highly restricted in what you can do fully autonomously. And that's where the human element of this human machine team also becomes extremely, extremely important. And the likelihood is that's your optimal output. That's your optimal arrangement. But evidently, when you look at each box individually, actually the level of transparency required is probably not all that high, in fairness. But indeed, when you then start to look at the sum of all the parts, and you're then leading to an output, a single output, then clearly you need to understand where potentially some of the deficiencies or shortcomings might come from.
Yeah, thanks, Chris.
Can I jump in there?
Yep, this is the last question then.
Oh, sorry. I think it's pretty clear to me that transparency is required in order to explain why decisions were made after the fact, and also to be able to communicate with human collaborators during a particular operation. But the big sort of research question for me is how should that be done? And I think that's the more important question. How do we make these systems not transparent, not whether they should or shouldn't be transparent?
Mm-hmm. Yeah, that's a good point. That's a really good point. Okay, well, I think we've unfortunately run out of time. There's loads of questions that we haven't quite answered. So we myself, Chris and Alan will go through those questions and send across the answers at a later date, as we did before. So apologies we didn't get around to answer them, but we will follow them up. Just what I'd like to say before we finish off, thank you very much everyone for their time today and joining us on a very cold and miserable, well, I suppose it's not that cold, but still miserable outside day. If you'd like to know more about this topic, then please, we'll send out the paper in an email after this session. And if you would like to know more, you'd like to know about our other webinars and podcasts, please go to our website and go to the Signal site. So that's bmt.org/signal. And then you can find the full list of our webinars, previous webinars, podcasts, all sorts. So that's a good place to go. So thank you very much, everyone, for attending, and to our speakers, and hopefully see you at the next one. Thank you.